Hello, everyone. My name is Matthew Reinhard. I'm a PhD student at the University of Florida, and today I'm going to be talking about computing the trispectrum in Axion inflation and some of the techniques we use to reduce the dimensionality of the loop integrals involved. So I'd like to start by defining a parity transformation, which is an inversion of all spatial coordinates. So at the bottom left here, we see a parity transformation acting on a coordinate vector, and it causes all the coordinates to pick up a minus sign. An example of a parity transformation we're all familiar with from our daily lives is looking at ourselves in the mirror. So here we have a right-handed coordinate system, and its mirror reflection has the z-axis inverted, making this a left-handed coordinate system. So this is why when we look at our right hand in the mirror, it appears as a left hand. So a central theme of what we'll be talking about is whether or not the large-scale structure uh, respects parity. And so one of the largest galaxy surveys that's been done is the Baryon Oscillation Spectroscopic Survey, also known as BOSS. BOSS is a fiber-fed spectrograph with 1,000 optical fibers, and it measured the distance to 1.5 luminous red galaxies. So this image on the right shows a lot of BOSS galaxies. Each dot represents a galaxy. The redder the dot, the farther away the galaxy is, and the more yellow dots are closer. So we know that the universe is highly homogeneous and isotropic on large scales, but what about handedness? Are there more right-handed or left-handed configurations of galaxies? So we can define the handedness of a configuration of galaxies in the following way. Let's imagine sitting on a galaxy. That'll be this red dot here. We'll call that our primary galaxy. And we draw vectors from our primary galaxy to three other galaxies, where R1 will be the vector to the closest of the other three, R2 will be the vector to the next closest, and R3 the vector to the third, the farthest of the three. And now we see that we build a tetrahedron with a galaxy at each corner. So if we trace around this tetrahedron from R1 to R2 to R3, we see that we move in a clockwise fashion. But now if we look at the mirror reflection of this tetrahedron on the right here, and we trace around it from R1 to R2 to R3, we move in a counterclockwise fashion. So each of these tetrahedra have a well-defined parity. You cannot rotate one into the other. They're related through a mirror reflection or a parity transformation. So another way of asking whether or not our large-scale structure violates parity is, are there equal numbers of right-handed and left-handed galaxy tetrahedra? So if we want to measure whether or not the large-scale structure violates parity, we can use the simplest statistic sensitive to parity violation, which is the 4-point correlation function. So if delta is the uh, density fluctuation field, which measures the deviation from the average density, we can compute the 4-point correlation function, the galaxy 4-point correlation function, in this way, where this integral is correlating these deltas at 4 different spatial locations, essentially adding up all possible different galaxy tetrahedra combinations. And this measurement was done in 2022 by Jamin Hao, Zach Slepian, and Robert Kahn. They found evidence of parity violation at 7.1 sigma, and Oliver Philcox also did this measurement and found evidence for parity violation at lower statistical significance of 2.9 sigma. So if this measurement turns out to be correct, this could have really profound implications for fundamental physics, because we know that all fundamental interactions are parity-symmetric, except for the weak interaction, but the weak interaction is weak and didn't play any significant role in the formation and evolution of a large-scale structure of matter. So any parity violation in the large-scale structure very likely came from new physics early on in the universe. A parity violating interaction during inflation could potentially seed the parity violation that we see today. So a little background about inflation. Inflation was a period of exponential expansion of space in the very earliest moments of our universe. This expansion is due to a field known as the inflaton field. And so phi will represent the inflaton field here. We can write it as some homogeneous background value plus small perturbations on that background. And inflation occurs because the inflaton field is, we say, slowly rolling, meaning the potential is suitably flat so that the inflaton field moves very slowly and its kinetic energy is much smaller than its potential energy, causing space to expand. And these small fluctuations in the inflaton field uh, provide a potential explanation for the temperature anisotropies in the cosmic microwave background and could potentially seed these overdense regions could seed the formation and evolution of the large-scale structure. So the standard picture of inflation does not have any parity violation. So we're going to look at an alternative inflationary model, which does have parity violation built in. So this model is known as Axion inflation, and I've given the action here for Axion inflation. Uh, we have the Einstein-Hilbert action, the kinetic term for the Axion field, which in this model is the inflaton field itself driving the expansion of space. This F mu nu is the field strength tensor for a general gauge field, A mu, which is not necessarily the electromagnetic for potential, but some general Ewing gauge field. We have the potential for the inflaton field and an interaction between the inflaton and the gauge field. And it's this interaction that really introduces parity violation into the 4-point correlation function. So just like before, we can write our inflaton field as some background value plus small perturbations on that background value. And we can separate these small perturbations in the inflaton field into vacuum fluctuations and fluctuations due to an inverse decay process where two gauge quanta can combine to form inflaton field fluctuations. So that scenario is depicted down here, where in red, those will be the gauge quanta. They combine and form axion particles. And these fluctuations in the inflaton field correspond to fluctuations in the energy density in some region in space, which correspond to curvature perturbations, which we will talk about in a moment. So focusing on the gauge field for a second, we can decompose it in Fourier space in this basis of circular polarization vectors, which are also helicity eigenstates. So this sum over lambda is summing over positive and negative helicity states. And A will be the gauge field mode functions. We can write down the equation of motion for these mode functions. And the solution to these equations show that we get a growing mode for the A plus modes and a suppressed mode for the A minus modes. So this imbalance in these two modes corresponds to a production of positive helicity particles compared to a suppressed production of the negative helicity particles. So this is the source of parity violation in this model. So for fluctuations in the inflaton field, we can also decompose this in Fourier space in terms of these Q mode functions. And the equations of motion are given here. So we have a homogeneous solution to this equation that corresponds to the vacuum fluctuations. And we also have a particular solution given on the right here by integrating this source against a Green's function. And the source function is given down here. Notice that we have a dot product of these two polarization vectors. And each term contains two creation and or annihilation operators and two gauge field mode functions. So we want to compute the Fourier transform of the 4-point correlation function, which is known as the trispectrum. And we want to compute this correlation function of the primordial curvature perturbations, since these can be translated to the late time galaxy 4-point correlation function. And so to compute the trispectrum of these curvature perturbations, we get several terms, but only this last term has any parity odd contribution. So our work is focused on computing this last term, which, if we recall from the previous slide, the inverse decay mode functions here correspond to the particular solution, which we integrate the Green's function against the source function. So that's how we get this last term down here, which are these. So we'll have to compute this correlation function of these four source terms. And each of these source terms contains creation annihilation operators. So we have to consider all of these possible combinations of creation annihilation operators. And there are only 5 of them that give a non-zero result, and they're listed here. And so now we have to consider all the different ways we can contract these creation and annihilation operators, where a contraction gives a delta function, shown at the bottom here. And these contractions can be represented pictorially in the following way. So here, the external momenta are given by these black lines, these k. The blue we'll call singular momenta. They have the loop momenta, and notice these red internal lines have a k minus q, which we'll call compound momentum. So contracting all creation and annihilation operators will correspond to a diagram with all of these internal lines connected. So there are 4 different ways of contracting the red and blue lines. So we call these connection structures. And it turns out that all of the different diagrams fall into just one of these 4 connection structures. There are actually 48 possible diagrams, 48 non-zero contributions to the trispectrum, which correspond to the non-zero ways to contract all these creation annihilation operators. So they all fall into one of these 4 types. So what we do in our work is we arbitrarily pick one diagram to represent each connection structure. We call these reference diagrams, and they're shown here. And each diagram gives a particular set of 4 delta functions. So let's focus in right now on just computing the contribution to the trispectrum of reference diagram 1. So computing this correlation function of these 4 source terms for this diagram, we get this fairly complicated set of integrals here. And naively, we might think that we could just integrate out these delta functions to simplify our problem. But if we do that, we get this expression where we have these the external momenta and the loop momenta, k and q, are mixed up in the arguments of all these mode functions. Um, so this is really not feasible to do analytically. Um, I mean, if we think about all the different, if we think about doing this numerically, let's see, there are four uh, external momenta, k1 to k4, but we could argue that one of those is fixed by the other three due to this delta function. So really there's three of them, each with three components. That's a grid of 9 parameters we have to integrate over, plus each of these four tau conformal time. So that's 9 plus 4, that's 13. And then we're integrating over the vector q1. So we're integrating q1 over a 13-dimensional grid, so we could call that a 16-dimensional integral. So this is numerically very intensive, and for that reason, much of the parameter space currently remains unexplored. So taking a step back, instead of integrating out the delta functions, um, what we instead do is we rewrite the delta functions as integrals over complex exponentials, and then we use the plane wave expansion to replace these complex exponentials in terms of these sums of spherical harmonic spherical Bessel functions. And what's nice about this is we get these four separate momenta integrals, and they all are pretty much identical, save for exchanging some subscripts. So now our focus is on computing these loop momenta integrals. And these integrals are actually convolutions. So we can use the convolution theorem on this integral to turn this into a problem of computing Fourier transforms. And it turns out that the angular parts of these Fourier transforms can all be computed analytically using this nice formula from Gradstein and Reisig. And we're left with just the radial parts of these integrals. And after performing some changes of variables and defining some other functions that I'll leave out for this talk, we end up with this expression here for the contribution to the trispectrum for reference diagram 1. But for any other diagram with connection structure 1, we can obtain the final result by just taking this expression and swapping the momenta, the external momenta from this diagram to get the other diagram that falls under reference diagram, that falls under connection structure 1. So in computing the this final result for each of the four reference diagrams, we can quickly write down the answer as well for any of the other diagrams that fall within that connection structure for that reference diagram. So all of the dependence on the magnitudes of the momenta are given here in this tau function, which is given at the bottom here. And this tau function and the ones that we get for the other three reference diagrams, they're at worst 6-dimensional integrals. So we have a really huge improvement in the numerical complexity of these integrals. So in conclusion, we've drastically reduced the dimensionality of the integrals involved in computing the primordial trispectrum for Axion inflation. Our next step is to numerically compute the trispectrum for a wide range of wave vector combinations. Then we will translate the primordial trispectrum into the late time galaxy 4-point correlation function and ultimately constrain Axion inflation using data from the dark energy spectroscopic instrument, which is the latest and biggest galaxy redshift survey. So thank you for listening.